Hello there and welcome to A2 Maths from Specimen paper 2, and here we're looking at question 8. Looks like it's a differential equations question. So a bowl is modelled as a hemispherical shell as shown in figure 3. Initially the bowl is empty and water begins to flow into the bowl. When the depth of the water is h, the volume of the water v is according to the model v equals 1/3 pi h squared brackets 75 minus h. The water flows into the bowl at a constant rate of 160 pi cubic centimeters per second between 0 to 12 h. So h here is centimeters. Find the rate of change of the depth of water. Okay, so we need to now combine two different rates of change. The rate at which the water is flowing into the container, dV by dt, is going to equal 160 pi. We could work out what dV by dH is by differentiating this thing here. Let's expand the brackets on this thing here. It's going to be 1/3 pi h squared times 75. 75 divided by 3 is 25, so it's going to be 25 pi h squared minus 1/3 pi h cubed. Now when we differentiate this, we're going to get 50 pi h minus pi h squared. Now what we want to find is the rate of change in the depth of the water, so that's effectively dH by dt. What is dH by dt? Well, we can work it out if we do, well, what we need is a dH on the top, and we need to multiply it by something that has a dt on the bottom. I suppose what we could do is we could flip this second one upside down and then have dV by dt on the second fraction here. So dV by dt, that's going to be 160 pi. What you can see happening here is that the dV's will eventually cancel each other out, as if you think of them as fractions, and then we're ending up with just the dH here and the dt here. But what we do need to do is the dH by dV is upside down version of this thing here. So it's going to be 1/50 pi h minus pi h squared. Hopefully what we can see is we've got pi's on the top and bottom, so we can cancel both of those out. So it's 160/50 h minus h squared. So find the rate of change of the depth of the water. That's this expression here. When t equals 10, right, so let's substitute 10 in now. So it's 160/50 times 10 minus 10 squared. That's 100, so it's 500. Take away 100, that's 400. So 160 divided by 400. Let's do the calculator just so we don't make a mistake. That's 0.4 centimeters per second. That's the rate of change of the height when the height is 10 centimeters. Right, now moving on to part B then. Given that the flow of water into the bowl is increased to a constant rate of 300 pi centimeters cubed per second in between the height of 12 and 24, find the rate of change of the depth of the water in centimeters per second when the height is equal to 20. Okay, so we're still looking for dH by dt. We're still going to calculate this by doing dH by dV times dV by dt. The only difference between this thing and the last thing was that the rate of change of the volume is now going to be 300 pi. So what did we get as, it was 1/50 pi h minus pi h squared. That was the upside down rate of change of the volume with respect to h, and then we're going to times this by 300 pi. So the new rate of change as the volume goes into the water. So cancel out the pi's from the top and the bottom, and we end up with 300/50 h minus h squared. We now know that h is equal to 20, So therefore 300 over 50 times 20, that would be 1000. Take away 20 squared, that's 400. So 1000 take away 400, that's 600. That's going to be 1/2, or in other words 0.5 centimeters per second is going to be the rate of change of the height when the height is equal to 20. So there we are, that's the answer to question 8 there, 7 marks for that. It's combining two different rates of change, and remember, when you've got two rates of change, you can always flip one upside down just so that the fractions then make a correct mathematical statement once you've differentiated. So there we are, 7 marks for that question. Let's now move on to question 8.